All right, hello everyone. I'm Professor Caudill, and we are continuing with uh, motion along a straight line. So velocity, particle gives its direction. So when we talk about velocity, we give a direction. Speed is the magnitude of the velocity. All right, so yeah, so speed is the absolute value of the velocity. Okay, so check our understanding. So given xt is -3 t squared meters, what's the velocity? So that's the position function. So x is -6 t, x at so at 1 second it is -6 meters, and speed 6 meters. So is velocity ever positive? So um, at t equals 0, the velocity is 0. I don't know. Most people probably would not say 0 is positive, so I'm gonna say no. Let's move on. So average instantaneous velocity. So now we're just going to get right into second derivatives. So I'm curious about the vector nature of velocity and acceleration. That's what I'm most curious about. Explain the difference between average acceleration and instantaneous acceleration. So I'm guessing that's just similar to velocity. Okay, so accelerate means to speed up. I like thinking of acceleration as change of change. So there's a lot of physics analogies that use acceleration. So average acceleration, it is indeed like the velocity. V final minus V naught T final minus T naught. A is average acceleration. So A is in meters meter per second divided by time in seconds. Time, okay. Meters per second, time in seconds. It's kind of redundant, isn't it? Time in seconds. Okay. Yeah, that's not what it's saying. It's saying time in seconds. Let's see. Meters per second per second. How many meters per second the velocity changes per second? So it's pretty much just building off of each other. So you see it's moving in a velocity, and that velocity is getting affected by a force, counterforce acceleration. So I wonder if they will describe the total motion of the train as a resultant vector. So is motion of the train some resultant vector that's what I wonder. 'Kay, so we have racehorse has a velocity equals meters a second. Um, 15 that so we're finding average acceleration. It's just going to be, it's going from the final is 15, the initial is 0, final is 8 seconds minus 0, so it's going to be whatever that calculated is. So first we draw a sketch. So they added the negative sign. We could just do that at the end. Um, I mean, they're gonna get 8.3. And this is the same thing as negative 8.3 because you can just pull out the negative sign, and I'm just describing the same thing. So that's kind of interesting. We see later means its magnitude would require to hold with a force equal to its weight, equal to his weight. Okay, check our understanding. Protons in a linear acceleration of protons are being accelerated and linear accelerator. Okay, so average acceleration is 2.0 times 10, 7, 10 to the negative 4. So because 2 is less than 3, we're gonna round it to 7. So we're gonna get 10 to 11 meters a second squared. And so this, see that now the book's contradicting itself. It didn't give us a direction. Um, is it going this way or is it going this way? It should really specify it. So we're going to correct that and just write I hat. So 10 to 11 meters per second squared. It's average acceleration. So instantaneous acceleration is second derivative of that equals first derivative of the position function. Or you can call that x t, whatever. I mean, it could be s of t as well. Okay. So the textbook doesn't really go into the definition of derivative. Oh, no, it did earlier. I lied. But it doesn't really explain limits. Limits, even I don't understand the full definition because there's several layers of it. Um, it's pretty gets pretty advanced math when you're trying to like formally describe what a limit is. So there's, I would say, 3 levels. One doesn't go into it all, one partially, and then another very real analysis type of deal. So all this is pretty much the same as velocity. It's just changing it. So let's do an example. Particles in motion and accelerating. V equals S. So these are all the same ways of writing velocity. So here we have V is 20, T minus 5, T squared. So A is 20 minus 10T. And again, they're omitting the direction. So like they call these vectors, but sometimes they just don't even, I don't know. I wish they would be consistent. So functional form, sat, instantaneous velocity. Okay, so you want V at 1, 2, 3, 5. Okay, that's 20 minus 5. That's 40 minus 4 times 5 is 20. That's 60 minus 9 times 5 is 40. 9 times 5, 45. And 100 minus 25 times 5. So we're going to get 15, 20. Is this one right? 3 squared is 9. 9 times 5 is 45. 60. Okay, is this one right? 40 minus 2 squared, 4 times 5 is 20. Okay, I guess these are all correct. What about A at so that's 20 minus 10, 20 minus 20, 20 minus 30, 20 minus 50, so 10, 0, negative 10, negative 30. Okay, so it's saying here they're going the same direction. Here, I think they're going the same direction. Here, they're not going in the same direction. Here, they're not going, they are going in the same direction. So, Hmm. Acceleration, velocity, and acceleration are negative. This is positive, this is negative. So I was wrong, I guess. They're in the same direction but slowing down. Okay, so it's when the velocity crosses the x-axis. Or I'm sorry, the y-axis. No, x-axis. Um, so if we draw it, it's going 15, 20, 15, negative 25. So reverses this direction here. So thinking about um, calculus with motion, that's kind of new for me. Um, so it's when the velocity becomes negative, there's a reverse of direction. So airplane lands on a runway, so east, so it's going this. Say each arrow is 1 second. So it's coming down. So describe its acceleration. So its velocity looks like this. Okay. Um, it's not going backwards. So acceleration starts here and it starts going down. So acceleration, I think it would be something like this. Might not be totally accurate. So here's some popular acceleration. Cheetah, 5 meters per second cube. Gravity, 9.8 meters per second cubed. This is probably the most important one here. I would guess. Electrons go very fast. So what's going on in this graph? So learn about position and velocity graphs. All right, let's do it. Graph system is initializing. The moving man is starting up. Man, this looks like something from the 2000s. Okay. Whoa. Okay. Okay. It's a little dated. All right, he's moving. All right. So I don't know if this is even right. Um, I think I broke it. Um, if V is 0, V or A, V is also 0. So over time, he shouldn't be moving. Um, okay, maybe I'm wrong. We're actually saying it's 10 meters per second squared. So how do you go from this to this? You do something called the integral of V d t. So if it's 10, then that is 10t equals V. So V equals 10t, V equals 10. So what this is really saying is ten meters per second. This should be the same as that. I think. All right. Let's move on. Acceleration, displacement, single body motion, and then two body motion. Taking the initial time, 0. So that's great simplification. So delta t equals the final time. X minus t0. Acceleration is constant. Okay, so what does it mean? A equals A if and only if V equals some number, let's say K, KT. Because when you differentiate V, it's going to be 1 times K T 1 minus 1 equals K T0 equals K, a constant. So if it's like that, then it's very simple. Okay, so displacement and position from velocity. So we know delta x, delta t. So they're doing some stuff and they're getting x naught plus average velocity times t, which is so this is like a number. It's not a function, I would say. Or I don't know. I'm seeing it as x naught plus kt, where k equals v So I've seen something like this before where policeman sees car going 40 kilometers an hour, and something happens where car gets, let's say 100, let's say 40 kilometers an hour. Let's say car goes 50 kilometers in 1 hour. And let's say speed limit is 40 kilometers an hour. Can the policeman pull over the car? So the answer is yes, because um, this implies car accelerated over the speed limit, because you can't go faster than that. Um, all right. So we can write A is V minus the initial, which is where I guess I could write it as K. I could keep the K notation. Which means V T equals V naught plus KT. Oh, okay, so earlier I messed up. So what is this? That is C for a constant. And if you recall, I did this integral. So what am I missing here? I'm missing plus C, because when you take an indefinite integral, indefinite into in gives a constant. Now what's a definite integral? Definite would be like taking from 0 to 5, 10 dt. We're looking from 0 to 5 seconds. Then that would be 10 t at 5 minus 10 t at 0, which would be 50 minus 0 equals 50. So what is this saying? It's saying you go 50 meters over um, if this is your velocity, 10, if you're accelerating. If you're accelerating 10 meters, if you're going 10 meters per second, then in 5 seconds you go 50 meters. Okay, so v t equals kt plus c is another way of writing this. So let's say airplane lands. Okay. Okay, then it accelerates. So it's still going v, but then it's going to get a counter force this way. 1.5. So phi t equals 70 plus so we just do v at and that should be negative 1.5. Final velocity depends on how large acceleration is, how long it lasts. Okay. Combine previous equations to find a third. Final position of an object experiencing constant. So if we know the initial velocity, we know how long. If we know the initial velocity and we know the acceleration and we know how long it's accelerating for, then we can find v. And its average velocity is 1/2 at. So this kind of throws me off because I thought v equals t, but no, it's a. equals A not V equals displacement and where is that displacement? All right, got 13 minutes left. Calculating displacement of an accelerating object. Okay. So how far does it travel in this time? Okay, so we want to find x. We know v naught, so I think v naught is 0 plus okay. So I think it's going to be something like that, right? Okay, 1/2 26 times 5.6, 402 meters. All right, so this probably, I feel like this is going to be in like a homework question. That's very, whenever there's something that makes something more simple, definitely be in a homework question, I think. All right, so solving for final velocity. Substituting this into that. All right, so they're not really explaining much here, but they don't explain it at all. They're just kind of like, okay, this is final velocity from distance acceleration. Yeah, I don't know. Calculate the final velocity without using information about time. So So starts at rest, that's 0. That's 402. This is 26. So that's 4 times 26, 52. So it's going to be square root of that. So this, I've argued with teachers over this. Some will say square root implies positive. Um, like I know what it's saying. You could just say, well, square root of 144 is 12 or negative 12. I don't know, maybe my teacher was a little too old. I don't know. We'll examine this equation. All right, so we're putting all this together. Try not to get lost. I think I'm hanging in there though. Be aware these equations are not independent. Finite time. So how far does a car go? So a car can accelerate opposite to the motion. So a car can do A equals negative 7. A on dry, A on wet is negative 5. Find the distances necessary to stop a car moving. So if V is 30 meters per second, so we want to find distances. So we don't know T, right? Okay. So 30 squared plus is the initial velocity 30. Don't know time. We don't know time. Okay, I'm gonna say 30 plus 2. Let's just do the dry first. Let's say x. Let's say we start at 0, so this 2x. So it's going to be 870 divided by negative 14. It's x. See if I'm close. Okay, so they did use this one. So I want to know what they used for V naught. V naught, they did use 30. V is 0. Why did they use V? 0. Okay. So they get negative 30 divided by 14. So this should have been negative 30. And that would have given us that. Okay. Okay. Let's finish this section. So the answer, we need to calculate how far it travels during this time. .5 seconds. Where? Oh, I see. Find displacement. 0.5 seconds. So if it's um yeah, kind of getting I'm gonna need to stop here soon. Displacement found. Reasonable. Unknowns. Unknown. So all right, so let's end it there. This is a lot to cover. I can see how this could be really struggling, difficult for some, but next time we'll pick up with this example and hopefully we build upon what we've learned. So thank you guys. I'll see you next time.